All right, so in this video, I'm going to be going through the dataset loan data that I went through in the previous video, where I was plotting some visualizations for the purpose of trying to tell a story as to why some customers uh, fail to pay back their loans. I was trying to pin my analysis on the actual given features here and trying to find the features which you can say are most influential or those which shed more light as to why customers fail to pay back their loans. In this instance, we would really want to build a machine learning model that we can take back to our client and say, look, if a customer presents with certain features before they take a loan, their credit score is X and so on. Therefore, such a customer, our model predicts that they are high risk. Or we want this model that we are about to build to tell our client while the customer is still in the loan repayment period that this customer is slowly inching into what we would describe as the dangerous quadrant, or they're becoming high risk. So in the previous video, what we did was to plot some scatter plots here. And one of the last plots that we plotted here was this 3D plot where we're trying to find ourselves a decision boundary. So we're going to be building ourselves a support vector machine. And when we look at how a support vector machine works, we are trying to find ourselves the best decision boundary. If we can locate a decision boundary by just observing our data, then what we can expect is our model will quite easily find that decision boundary. So we cannot find the decision boundary based on these features here. So what we will do, we will proceed with building a support vector machine, and we will check how it performs based on this data, based on these features that we have in front of us here. So the main purposes, of course, of this video, we want a support vector machine that works and that gives us correct information, but also we want to build ourselves, or should we say, we want to train ourselves to follow the correct procedures as far as building a support vector machine or any machine learning model for that matter. We want to ensure that we follow sound mathematical principles as far as our data is concerned. Do we need to normalize our data? Do we need to standardize our features? Which features do we insert? And what output does our model give us? And also, we're checking what parameters do we insert? Do we need to tune our model after it has been trained? So what I'll be doing is I'm going to be working on the Jupyter notebook, and then I'll be building the model there, and then we can take it from there. I'm going to import our main libraries. So it's going to be NumPy, Matplotlib, Pandas, and Seaborn. I'll upload my dataset as a Pandas data frame. I'll say pd.read.csv. The name of the dataset is loan underscore data.csv. And let's check the head of our data frame, df.head. And then also let's check the info of our data, so df.info. All right. So now what we're gonna be doing is we're gonna check the effects that standardization has on our data. If we go back to what we had here as far as the 3D plot, we see that for the variables which I determined to be most influential, their actual ranges are not the same, and their magnitudes and also their units are different. So if we're going to be building a support vector machine, we will need to seriously consider feature scaling. And in this instance also, I want to check what effects does feature scaling have on my actual features here. So I'm going to define my features and my target variable as x and y, and then I'll take it from there. The end point of this short exercise, I want to recreate the hist plot that we built early in our video. So I want to see what effect does standardization have on our distribution, or on the distribution of the actual his plots. So what I'll do, let me define x. I'll say x is equal to df, and in here I'll put the columns of the column names of the data frame. To get the column names, I'll just say df.columns, run that, and then take the column names which I'm going to use for x. So it's going to start from credit policy to public record. So copy that, and I'm going to paste it in there. And I'll say dot values so I can get the numpy array from this. And I'll do the same thing for y. I'll say y is df, and I'll put in there the column name not fully paid dot values. Okay, so I've defined x and y. So what I'll do is I'll define a new x. I'm going to use this x for further analysis. So let me define a new x where I exclude columns which I will not standardize, and those columns will be the credit policy and purpose. So I won't standardize or normalize the credit policy because already the column is shown to be in a binary form. So it's either 1 or a 0. And if it's either a 1 or a 0, then I would want my model to interpret that data as it is, as either a 0 or a 1. So I'm not going to change this. I'm not going to change my purpose column because already it's in an object form. So I'm going to standardize from interest rate to public record here, because none of these are binary in nature. So I'll define a new x. I'll say x underscore is equal to x. I'll include all the rows, but for the columns, I'll start from column 2 to the end. And now I'm going to import my standard scaler. I'm going to say from sklearn dot preprocessing import standard scaler. And I'll create an object sc from the standard scaler class. So I'll say standard scaler open close parenthesis. Let's run that. Okay. And now I'm going to create a variable, and that variable is going to be the scale features of x underscore. But I'm going to give that variable a name. Let's call it xdf. And I'll say xdf is equal to the sc object fit underscore transform x underscore. Now I'm going to use this xdf to create a data frame so that I can plot his plots as seaborn by using seaborn. So I'll create this new data frame and give it a name scaled underscore df is equal to pd.dataframe. So in this method, inside of it, I'm going to insert the scaled features xdf, and I'll need to give this scaled df some column names. So those column names I'll just steal from what we had here. So I'll just say columns is equal to open close parenthesis is gonna be from the interest rate till the public record, and it should work in that manner. Okay, so now I've got my scaled underscore df. Let's get the head of this data frame. So those are my scaled features here, and if we check again the purpose that scaling that standardization has on our data is that it takes these values in each column and takes and changes the distribution whereby the mean becomes 0. So what we're going to do now is we're going to insert the all important not fully paid column here so that we can hue our distributions based on this not fully paid here. So for that, let's just insert that column say scaled df is going to be not dot fully dot paid is going to be equal to df not fully paid. So I'm just inserting this columns right into this data frame. And now what I'll do is I will copy paste from what we had here. Here's our command there. Let's copy and paste it there. And now let's attempt to play this and see what happens. Okay, all columns is not defined, so let's define this variable all columns, which will be the column names that we would want to plot. So all columns is equal to, let's take this guy here, copy paste him right there. So this is our original hist plots from the previous video. So this is from the previous data frame. So now we're going to plot the same features, but now from this new data frame. So I'll just change the name of this df to being scaled underscore df. And let's see what effects the standardization has had. So again, the standardization assumes that, of course, your data follows a Gaussian distribution. So standardization works well for data which already is in its normal distribution form. For example, if you look at log annual income, the mean is at 0, and now we've got equal what we call standard deviations on the left and on the right. So that's what you'd want to see. But based on most of these features here, interest rate, installment, and the like, there doesn't seem to be any effect that the standardization has. Well, we can see some minor differences there, but standardization does not change the distribution. It just changes the actual values that we have. What we want to do, we want to now focus our efforts on these features: the revolving balance, the inquiry last 6 months, delinquency, and public record, and see if we can normalize this information. We cannot standardize data which is not already in its normal, which does not follow a normal distribution. Can we normalize this? Can we take down the number of representations? If we check the revolving balance, we've got from 0 to whatever number here, which probably it reaches into the high 30s here. Can we reduce the number of representation here? Because if we have a single value here having a high number of entries, then it is going to affect our model quite significantly. We want to either change this into being a normal distribution or reduce the number of the number of representatives here. So what I'll do, I'll use the np dot log method for these 4 features in the next part, and then we'll see what effects it has. We'll just recreate this plot on the data frame that we'll create then. So let's create that data frame. Let's start first by making a new data frame, new df, and this data frame is just a copy of my df. So I don't want to normalize my original data frame. I want to normalize the new df. So now I'll use the np.log. So it's just going to give me the logs of these values here, and I'll plot the actual resultant. So for that, I'll say new df for revolving balance. I want that column to be equal to np.log new underscore df, the very same revolving balance. So I'll do the same method for these other 4, and we'll take it from there. All right, so there we have it. We've updated our new columns there. Now, what we're going to do is we're going to copy and paste this code onto here. And now I'll change my data frame here to being the new data frame, so new DF. All right, so let's run this. And that's what we get. So revolving balance, notice now that of course it's been normalized. In query last 6 months, we've reduced now the number of entries from 0 to 50. Now it's from 0 to around about 3, the same as delinquency and public record. So we can proceed with this information as it is. So before we actually standardize our information for the model, we'll need to normalize it first. And after we've normalized it, then we can apply standardization. And these are the features that we will insert into our support vector machine. So now let's define a new X and Y based on the new data frame. We'll proceed with this new data frame. We'll just copy and paste this command here. And now, instead of df, I'll have it new underscore df. And now what I'll do, we had a case of, in the purpose column here, I have to go back to the head of the data frame, which I don't have here. The purpose column is an object, and it had about 7 unique categories, from debt consolidation, credit card, and so on. So I'll use the column transformer to change the data frame and create binary representation for all of these categories onto our data frame. So for that, I'll import the column transformer and one hot encoder class, and after that I'll perform the actual transformation, and I'll show the results after that. Okay, so I've imported column transformer and one hot encoder. I've created a new object here, the CT object, and I've specified that I want column number 1, position 1, to be the position where the actual encoding takes place. So I'll say X is equal to the actual CT object, and then give me back a NumPy array. So I'll play that, and it's going to give me a new X. So if we check the previous X's, what you call shape, if we run this again and then check X.shape, we've got 13 columns. If we run this and now check X dot shape, now we've got 19. So we added 6 more. All right, so after here, I'm going to perform the train test split of my X and Y. So I've performed the train test split. I've used a test size of 25% and a random state of 0. Next, I'm going to perform the scaling again, but only for values. Remember, we need to scale from interest rate to public record, and we want to make sure that we only fit the scaling object onto the training set. So we're going to say from sklearn.preprocessing import standard scaler. Now let's create the object sc. Sc is equal to standard scaler, and now I'll say x train. Now this is a NumPy array, so what I can do is I can slice this. I can say for all the rows of the array, but starting from position 8 to the last, I want now you to fit underscore transform. So I'll say sc dot fit underscore transform. Transform what? Transform the actual. And then x test at the same position 8 position 8 to the last is going to be sc dot transform. It's going to be transform the actual values there. There we go. So let's run this. Hope there are no typos. Okay. So now our features are ready now for the actual model to build the actual support vector machine. And for that, the support vector machine comes from the SVC class coming from the scikit-learn. So I'm going to be using the kernel, the radial basis function, because already we saw that just by using visual, like our visuals, we cannot define a decision boundary. So we're just going to assume that there exists no linear decision boundary in this data set as it is. Let's use just the radial basis function from the get-go and see what results we get from that. What I'll do, I'll say from sklearn.svm import svc. Now I'll say classifier, which is the name of, I'll give the model, is equal to svc, where the kernel is equal to rbf. Random state, I'll make it equal to 0. And then another important parameter that I'll add here is the probability, and I'll make this equal to true. A model might misclassify a client, but that model would want to ensure that if it gives us a probability that then even if it has misclassified that particular client, that probability, it might give us information if maybe the client is slowly inching their way into what we would define as the dangerous quadrant, or they're becoming high risk. So now I'll just fit the classify model onto my training set. Right. And we're going to run this. Okay, so we've got our model run. So now let's find ourselves the predictions. Let's make predictions. So we're going to say, we're going to give one prediction. So the one prediction will be the actual predictions that the model is giving us, and then another prediction will be the probabilities. The actual predictions, I'll make it ypred is equal to classifier dot predict the x test, and then another the probability prediction, I'll call it y prediction underscore probability is equal to classifier dot predict underscore proba x test, and we run that. Okay, from here let's output our accuracy and our confusion matrix. The confusion matrix is coming from the scikit-learn dot matrix, and also the accuracy score. Let's input those and run them. Okay, so those are results. The accuracy of the model is supposedly 84%. So the model got 84% of the predictions correct. Now, the customers who actually paid their loans, the model predicted them to be close to 100%, but for those who could not pay back their loans, the model could not find the prediction. So yes, it's giving us a prediction of 84%, but we will need to also put it in the back of our minds that the data set had a higher representation of customers who paid their loans. So in this case, we want a model which gives us clients who fail to pay back their loan. Can the model predict clients who fail to pay back their loan? In this case, it's a resounding no, and the 84% in this matter is just what we would define as a flattering number. But with that said, the y probability would probably play now another part now in this. Can we use the information from the probability to our advantage? Can we go back to the client and say, fine, our model could not predict clients who fail to pay back their loans, but can the model predict clients who are high risk based on the features that they had. Are the customers who failed to pay back their loans defined as high risk by our model? Let's find that out. What I'll do is I'll recreate the data frame, a new data frame where I will insert the probabilities into that data frame. So that data frame is only going to consist of the test set. So this data frame will be built on the information coming from the test set, and I'm going to append the Y prediction and the probabilities onto that data frame, and I'll analyze the data and see, does our Y probability give us any information? So the data frame has been created. So this data frame only consists of values which were part of the X test here. So these are the X test values, as I had to recreate them here with the same random state. So I've created my X test now. I've inserted my probabilities, my Y probabilities into the data frame, and I've concatenated them to make it easier for myself. So here we have the probabilities, as you can see here, 0.15, whatever. So the prediction 0 would entail customers who have got a probability of less than 50%. So if your probability is less than 50%, that you will fail to pay back your loan. So the model itself will predict that indeed you will pay back your loan. So now what we're going to do is plot a few visualizations to see, is this value useful for us here? So let me use SNS. So I'll say SNS.histplot, where my data is equal to df underscore pred, and then x is equal to probability, and then hue now is not fully paid. So these not fully paid are the actual what we can describe as, this is Y test, not fully paid. Okay, let's run this. Okay, let's limit our X axis now so that we can only see what's happening. It seems the probabilities, they range from 0 to 0.7. There's a peak here, so let's zoom in on that peak. Let me just copy paste this guy. Let's just plot it again, and then say plt dot x limit. I want my x to range from 0.1 to 0.2. There we have it. So now we've got the green and the blue. So the green is the not fully paid. The blue is the paid. Now what we would want to see is a bimodal distribution. So for customers who fail to pay back their loans, we would want their actual probabilities to differ from customers who pay their loans. We do not want to see the same group having sort of like the same mean. So in other words, we would want to see a distribution. If this model is performing well, we want to see a distribution whereby we've got a peak here of customers who paid their loans in full, and another peak later at a higher probability of customers who fail to pay back their loan. These peaks are occurring at the same time, and on the longer distribution, there isn't any other peak. A good performing what we call a model would have two peaks in this instance as far as Y probability is concerned. Let's plot another visualization. Let's plot a box plot to see if maybe indeed are they the same or not. So let's give that box plot a fixed size. Let's say fixed size is equal to 12 by 4. Now I'll say SNS dot box plot data is equal to df prediction x. I'll separate them on the purposes, and then y is equal to probability. I'll also hue it on the not fully paid. Okay. All right, so let's again do the same thing here. Let's limit our analysis here. Seems there's a lot of peak at one probability. So let's give it a plt dot y limit. Let's say starting from 0.1, and I want it to end at maybe around about here, 0.25. Okay, so the green is customers who fail to pay back their loan. The blue is customers who paid. So the model itself, if we check the outliers, okay, customers who fail to pay back their loan, do they have a higher probability as predicted by the model? As far as outliers are concerned, no. As we check here, small business, the highest probability is from a customer who paid back their loan. Debt consolidation, the highest customer again. Home improvement, the same thing. All other, the same thing. If we drill down now, we check the median. The median seem to say that, okay, fine. For most of our purposes, the actual probability is indicating that there are some customers who, in terms of customers who do not pay back their loan in full, their medians are slightly, but only just slightly higher. But there's not much you can make from this information. We just want to check, is our model at least heading in the right direction? And in this case, it seems that there isn't what we can say a definitive, say yes or no. The data in itself, as we saw, based on our visualization, the yellows and the blue dots here, we could not find a decision boundary just by looking at the data. It seems if we are to predict at a higher accuracy than the accuracy that we found here, we will need to have a data set having a much higher what you call numbers of customers. I think a larger data set, if we check this data, it had about 9,500 entries. So maybe if we'd have a data set with 10 times more, but we can be fairly confident that the procedures and the processes that we followed are mathematically sound. You could argue that maybe we should have normalized our data after we performed the test, the test split. That's one. But apart from that, it seems the actual processes that we followed are actually sound. It's just a matter of the data itself is too noisy, and we could not find a definitive accuracy that we can present back to our client, and not just the accuracy but also the probabilities. If again we check the FICO scores, there's this plot I plotted at the end of the last video where just on the basis of the FICO score, I was trying to get a percentage or a probability that the customer will not be able to pay back their loan, and we would have wished the model to give us sort of like similar features where, as we see from this plot, is highly definitive that a customer having a higher credit score, their percentage of paying back their loan is quite, the percentage of failure to pay back their loan is quite low. So maybe in the next video, what we can do is limit the number, we limit the number of features here. We do a bit of feature engineering. We exclude some features from our analysis and only focus on features which will give us a much better, we can say, result that we can present back to our client. But yeah, so based on that, yeah, let's we can leave this analysis on this point. And what can you say? Thanks a lot.